And so we are recording. Good morning and welcome. It looks like we'll have a couple more people join us as we get started, but I know that we have a lot to cover on our last day, and so I wanted to get us rolling early. And so I will throw it to Manley this morning to get us rolling.
Okay, let me start this. And Manley, I'll let you go ahead and get started.
Okay, well, welcome back, everybody. I hope you enjoyed the building project that we had. We're going to go to the next. You can see how to get up with us there still, and you sent us our stuff in. About the CEUs, those of you that have turned the homework in, and we're going to give you until tonight, was it 6 o'clock tonight, if you haven't done it, if you want the full credit. Those that are with us that have been joining us each of the three sessions, but did not do the homework, will get less credit. But if you want the full credit, if you'll do your homework by tonight or this afternoon at 6 o'clock, we can make sure you get the full credit. Oh, it says till 8 p.m. at the bottom. I'm sorry, Jude, I thought it was 6. We'll accept homework until 8 p.m. tonight. So get us that later if you can. And even if you have to build something later and take a picture, that's fine, and do a research plan. It'd mean more if you've done it already, but that's fine. Okay, we can go to the next one. If you got questions, you can ask us in the chat. I like to, Judy, what I like to do for a second is just go off the slides and just let them see me for just a minute. I'm doing this backwards from last night. Okay. Can you see what I got here, Judy?
I can.
Okay.
So
all right.
Everyone may want to choose the speaker view so you can see Manley.
Okay. All right. So if you'll see what I have, I want to do these ahead of time because you're getting ready to see some pictures of some of the towers that we had built. And I showed this last night afterwards, Judy, and it's hard to, if you have already seen all the pictures, it's hard to go back in your mind, and they didn't have them at that point. So I want to show you 2 or 3 things that you can apply as you're looking at the photographs today. Several people ask me, what do you do with the index card? Now, we had several sizes, so we did have some variables here. The straws. Here's a Hardy straw. I had a McDonald's straw last night. They're very thick and heavy, whereas straws from other places are thinner. And here's a McDonald's straw in the middle here. It's very thick. And these straws that I used for this one are a lot smaller. I don't know where these came from. I think we bought them in bulk. But anyway, so the straws were a variable, and the size of the index card. However, most people, as you see the photos later, maybe put the card at the very bottom or the very top of the tower. It wasn't as useful as it could be. What you have here is I have 2 straws, and a lot of the towers, especially middle and high, had a horizontal part of their structure and a vertical. They weren't worried about just having it tall. They wanted it strong. But if you tested your tower, it usually, when you overloaded it, it would rock to one side and collapse. And so an index card is not very strong this way. But if you try to pull it apart, it is very strong. So what I did is I cut the corner off this index card, and I matched the corner to a joint where 2 straws came together, and then I taped it on both sides. And now this is very strong. This would keep these straws from collapsing apart. And if you did this on the other side, I didn't do it on the other side, but if you did that on the other side of the structure and then going the other direction, so you had about 3 of these gussets, it would make this very strong. If you look at real bridges and real towers, you'll see thin plates of metal that are riveted at the joints like this, and they're a lot thinner, and that really holds the tower together. So that was one feature that when you look at the picture, I don't think you'll see a single gusset, none. Now, one thing you will see is lots of triangles. So you'll see a brace between 2 columns at an angle, which is a good thing to have. What would also be good is to have a brace going the opposite way, have cross braces, lots of triangles. The more triangles you can get in your figure supporting thing, usually the stronger it is. So this structure would be stronger if it had a brace going the other direction. And you'll see some pictures where they had braces maybe going one way, but not the other way. Also, there's one feature I wanted to show you. It's going to be hard to see on the screen, but it's hard. You probably found it hard to tape a straw to popsicle sticks. And so what I did is I took the straw on the very end of the straw and I cut it and made a slit. And then I slid the straw on the popsicle stick with a piece of straw on each side, and then just wrapped a small piece of tape around here. And that makes a very strong joint connecting these two together. What they would do in reality is they would have, lots of times you'll see this beam will have a piece of a plate on both sides that bolts the beam to this beam. In construction, they don't necessarily use different materials, but sometimes this would, if you go to the airport at RDU or some of the airports, this structure here is usually a thin piece of metal like a rod, but on the very end it has a plate that bolts to both sides of this, and that keeps this from pulling apart. So if the point of all this is, if you did a lot of research on towers and bridges, you would have discovered some of these features and might have been able to use them in your feature. Well, another thing, I saw string. Lots of times string was used to tie like straws together or whatever, and that was a good thing. Here I have a big loop of string, and if I had a structure like an elementary tower that I didn't want the bottom to flare out and go apart, I could wrap this string around the middle way, the bottom level, and pull it tight and then tape it at that level. So that way the string is very strong this way, and it would keep the legs from jumping out. So that, since you couldn't connect your tower, it had to be freestanding, that would be a good thing to do. Lots of little features, just some examples of features you could have added to the towers. Now, the reason we did this is to actually kind of show you how we would work with students and getting them to build some kind of structure. It's not that likely that your students are going to do a project where they build a structure like this, because we've been building for thousands of years, and there's been so much research in engineering, it's hard to come up with something new as far as a new way to build the structure, but it's possible. But we can come up with new materials and new ways to join them and put them together and whatever. And there are lots of, as you'll see in a minute, I have a slide, I'll talk about it then, lots of different types of engineering. Okay, Judy, we can go to the slides now to the, oh, I'm sorry, I got pictures. Let me share the
You
pictures.
got pictures.
Yeah, I'm going to share the pictures now, see if I can get those for you. It's probably the last one here if I can find it. There we go. All right. Okay, let me get this out and make this full screen for me. Are you able to see that okay, Judy? I may have to bring it down a little bit.
Yeah, I can see it
Okay.
now.
All right, so here's
You may
a,
want to go up to
here's
the
a-
top and get rid of your, where it
Okay.
says view, to view all the,
get rid of that.
yeah.
Anything else you want me to get rid of? No,
Well, you
that's
can
it.
get rid of that top portion. It's under view. Where it says show
Under-
tools or something like that.
Yeah, right here, right here. Shows
Maybe.
toolbar. I can hide
No,
that.
it's on the very top. So,
Oh, I'm missing it somewhere. Oh, well, I got my bar here.
yeah, don't worry about it. Just go on.
All right. Look, this first one's a good example. It was, they didn't tell me the height. Looks like it's about 2 straws tall. And by the way, straws is another variable. McDonald's straws are tall. Hardee's has a really strong, I mean, they're thick, McDonald's straws. Hardee's has a really long straw that's also thick that you could use. That would make a difference. If you were comparing one to another, you want everybody to have the same straws, which we couldn't do. But this one's 2 straws high, no gussets. And another thing is the strongest material you had would be popsicle sticks. Now, this person might not have had popsicle sticks, and so that's why they didn't use them. But if you have them, the students lots of times will put the popsicle sticks horizontal on the bottom just for weight. And really, they're strong, so your popsicle stick should be vertical, because that's the strongest thing you have, especially if you were building a middle or high tower. But anyway, no gussets here. You can see this tower is about to twist, and it wouldn't support much, and so it's hard to get it very tall. But if you had some gussets in there and some triangular supports, angular supports like I showed you, it would make, and look at all the straws in the background. So there are a lot of straws that could have been used for supports to keep this from twisting. I'll go faster on others, Judy, but this one's very tall, and I didn't home in on it, but it looks like it's about 5 feet tall. One problem is I see the sticks, and they look like tongue depressors, and there's a piece of index card or pay on the bottom. It's not really being used for much, but these were materials for middle and high school that we used to put on top for mass. They weren't allowed in the elementary one, so so this one would not follow the specifications that you had because it's got additional materials, and that is one of the reasons it can be so tall, because whatever that is probably very heavy. And here's one that's looks like that's about 6 inches, about almost 6 inches tall, which is not going to be tall enough. They had to be at least 30, and that's under 15 centimeters. Got some good design because it's got sticks going vertical. Of course, those are tongue depressors, I think, not popsicle sticks. And there are some horizontal, a lot horizontal. These you could have had another. This one could have had another level of popsicle sticks and been tall enough to support some weight on top of the cardboard. And then this index card could have been, a triangle could have been put here, and then on the sides going the other direction here and maybe over here, and that would keep this from, it would support a lot more mass. And there are also some straws that could have been used for reinforcement. So this tower could have easily been taller and would have been a lot stronger. We're going to see some strong ones in a minute, I think. I hope I'm not hurting feelings. We try to keep these anonymous, so you don't know who we're talking about. You may know, but now this one was 46 inches high. You can convert that to centimeters. And it is swaying, but it's standing. And it looks like it got it sitting on the cardboard. Now, if it's taped to the cardboard, you'd have to undo that. And you can't use the cardboard as part of the structure. It can only be put on top. But this one's pretty tall. And I don't know how tall this one is. This one's about 1, 2, 3, 4, 5 straws tall. So that's pretty tall. You multiply 5 straws. And you can see where it's weak. It actually has too much up here. If you're trying to get this tall, it'd been better to have had one of these, and you could have even gone taller, but just the weight of all these is pulling this tower over. And if this happened to be a middle school tower, I don't think it was, where you're going to add a load, you'd have to add it here. So that would be, the height would be from there down, not all this. If it's elementary, the height would be from here to here. And you see the popsicle sticks on the bottom? They were not used vertically, but they are heavy enough to help hold this down. It's amazing, I think, the standing, because it has so much stuff up here, so many things up there. Okay, let's go to another one. A little bit similar to that one, and it's leaning. Got a lot of, it does have some cross braces, and that's helping a lot. It's leaning, and one thing that would keep it leaning would be some gussets in places like there, and on the other sides, some of those little pieces. Index card, and the index card might be there, but it's not helping much. If it were cut up and pieces of it were used, this would be a lot stronger. And this one has no gussets, and really it might be upside down. I think it'd be better if you took this, made it the bottom, and flipped it around and put the cardboard would then be on top, and it might support more. And of course, this one needs cross braces and gussets. Needs some cross braces across this way. That will keep it from coming apart. There's your weak spot right there. So when you add a load to this tower, it's gonna bow and bend and drop. Everything's gonna fall because it's gonna bend right there. You really need something. Even the string would be good to tie from here to here. But a straw would be very helpful as a brace, a diagonal straw. All right, this one has a pretty good height. I don't see it on there, but also you'd have to untape that piece of cardboard. You're not allowed to tape the cardboard on the bottom, so that would take some of the, I think it would still stand up. But you could also put popsicle sticks on it vertical, and that would help hold it be stronger and heavier, especially a popsicle stick right through here. It looks like that's where it's going to bend, here or here. All right, let's keep going. And this one looks pretty good for elementary, pretty strong. They might could have even got a little taller. They got a flag up there, so you see it's like 1, 2, 3, 4, 5, 6 straws high. I don't think we have a measurement on that one. That's a pretty high one. That might be our highest one. But again, looks like the cardboard's down there. You have to take that cardboard out from under it. Pretty good height. You can see it's about to fall over, but it is self-supporting. They put a little brace right here maybe it's just something laid on the table, but it's barely that brace. That's the weak point. That needs to be pulled out this way some if possible to give a little more support. And the string would be good to have, and some gussets, especially on this side, keep it from collapsing. This is a pretty unique design, but it was pretty high, sitting on the table. It's got little skids there holding it up. They didn't use all the sticks. They could have used more sticks, would have been gotten it even higher. Some sticks in here for braces would be good. Okay, this one looks like it's pretty strong. It's got a cardboard on top. This is a middle school tower. One thing they could use is they need some cross bracing, diagonal cross bracing, like right here, and then going the other direction so that it doesn't twist and fall. And cross bracing across here. They got one cross brace here, but they need one going the other direction. So if they had one going like this and one going like that, they might be, I don't think they're out of straws. 6, 9, 10, 11, 12, 13. Yeah, and they could have used popsicle sticks, which they may not have had. That's one of the problems with doing this at home. Some of the students would not have popsicle sticks. And we got a couple different versions here. I think maybe the person made both. They made a middle school one, and I don't know if that's high enough. That might not be quite 30. And this one's pretty tall. I can't see all of it, so we can't really tell how tall that one was. I'm going to go a little faster because these are similar. Cardboard is at the bottom of that one. This one needs cross bracing. They got looks like a pencil laying on top, but and they use dowel rods instead of, and dowel rods are going to be a lot stronger than popsicle sticks, but none of them are vertical. And they got, look at all these that are left. This one, all these straws there could be support cross bracing. And gussets too, probably. Okay, let's keep going. That one's very similar. And then here's this one. Surprisingly, this one's pretty strong because it doesn't have a lot of cross bracing, but it does have a lot of straws. You got cross bracing down here, which is very helpful. And that one is at an angle. Got a couple at an angle there. So it's this is stronger, you know, stronger. It surprised me when I saw how they loaded it. I think this one has a load. Yeah, there's a tower. I'm not sure it's 30 tall because that's not a full length of straw and that's not a full length of straw. And it takes about 2 full lengths of straws to get 30. That's a heavy can of Progresso soup and then 3 cans of tuna. So it does hold up a lot. It needs to be a little taller probably. So whoever, don't know whoever that is, if it was 30 or not. This one needs a lot of gussets, a lot of cross, it's got some cross bracing. That one didn't have a load on it. There's another one. Okay, another, these are similar. These could have been straws and could have had the sticks going vertical. However, there are tongue depressors, not popsicle sticks, so they're a lot stronger. 2 very similar. This one has too many popsicle sticks. I think 12 is what we had, and you're going to count 30 or something. I don't remember how many are there, but there are a lot. All right, let's go. Here's another one that's similar to the one before. Not quite as many straws were used, and it is very strong. And they put these little braces out to the side to keep from tipping over, which was a neat idea. So they used, you know, some of their straws for that. I'm not sure how tall it is, but you got 2 cans of soup and 2 cans of pineapple. So this one is showing a lot of mass, maybe the most we've seen on top of one. I'm just showing some from a workshop we did, some teachers building one. And that's it, Judy. So I'm going to, let me stop that share. And if you want to go back to the slides.
Okay, we had a couple of people that were having trouble getting in, so I think I sent messages to those. So anyway,
All right.
so I'm gonna
Go to the next slide. Now, I hope that was helpful. I hope all that was helpful. If you do some type of engineering project or have to do some kind of build, they can then learn about a lot of variables they didn't foresee. And they might not be doing a structure, but I had some students that were working on one of some kind of structure they were going to build across a river or a stream to collect garbage, so and they could clean it every now and then so that garbage wouldn't get downstream. That is a bit of a build, and by building other things and practicing a little bit, they can begin to foresee some of the things that they need to look into the research to learn more about their build and about the variables and whatever that are involved. And so, but there are lots of types of engineering. If we can see in the next slide, well, that's okay. This slide's good. I was thinking the next one, but that's okay, G. My mind jumped ahead there. But here's the whole point. This slide is very important. And you'll have the slides. You need to look at this. If students doing an engineering project, they need to make a case for why that problem that they're trying to solve is important. They shouldn't be just making a model of something maybe that somebody else created. They might find a creative solution that somebody else has come up with somewhere that people may not seem to know a lot about. And they go, oh, I'm going to make a model of that and show and teach everybody about this creative solution. Well, somebody's already done that. And so what they need to do if they're going to do an engineering project is find out what other people have done. And they got to make a case for why they're doing the project, solving that problem. And most likely they're going to propose newer, different materials or a design. And so they have to come up with a design that's different for a reason, or different materials. And either the design might be stronger or easier to construct. The materials might be less expensive, but just as strong, or maybe even stronger. So they make a case like that for why they're doing it. And they're going to have to compare that to what's already been done. So they need to build accurate models, and they need to be realistic. Sometimes the models, if they're not realistic, they actually draw the wrong conclusion because their model has something in reality that would be a lot thicker, like a 3-foot beam, and they aren't spending the money for a 3-foot thick beam somewhere of steel. And so they need to be realistic, both the example they're comparing it to and the one that they've built. And they got to test their idea, and they got to test it till failure. They're going to revise it and retest it. And then in the end, you can see that at the bottom, the last one, they got to explain why their way is better. That's the whole point of an engineering project. So this slide is very important. Okay, let's go to the next one. I think I got some. These are just some example ideas, getting away from just the structure that we practiced. Like in North Carolina, it'd be important to maybe, if you could design a hurricane-proof house, and you come up with some different ways of designing it and building it that people haven't done before, or reducing coastal erosion and so on. These are just examples, but they can be approached. There are lots of different projects could be done on reducing coastal erosion. That hasn't been solved. That's a problem that continues, and we have some more. And let's take the first one. I'm just going to do the first one here. If somebody's going to try to do an easier way to lock lockers at school, they're going to have to show how their way is better. So they're going to have to look at a lot of lockers and how easy it is, and come up with a way to measure maybe how easy it is or how hard it is to unlock traditional lockers. And then they're going to have a locker. The locker has to be just as good as traditional lockers, if not better, but it needs to be easier to lock. And they got to have a way to measure that. And you see here's some other examples. And it's beneficial with your students to use examples like this and talk through them with them and let them decide how would somebody have to measure something. How would, what would they have to do to show that it's better than existing ones? And students don't like to do the research. They need to do that. It's very important because they need to know what's already been done. So the research is one of the first things that they're going to do. Okay, Judy, I think we're going to shift gears to the research plan.
Yeah, I'm going to talk a little bit about the research plans briefly, and I've been getting them in. I've been looking at them, and I will, I have vowed to myself, I will send you comments back on your research plans, but have not had a chance to go through them all at this point in time. But what I would like to do right now is open up the chat and get some comments back from you about what you found out with your research plans. So if you will give me, actually, there's so few of you. How many? We don't have that many. We've got 10 of you.
If they want, Judy, if they want to chat, they might want to chat about, you just let me know how they like that project we did. I'm sorry, I should have said that. But yeah, you're right. I think we could let them talk now if they want to, if everyone wants to unmute and say some things about their plans. Sorry.
Yeah, because it's 10:24 now, Manley. So any comments that you would like to say in your chat about building the tower? Because I know you didn't do that.
Yeah, and I can come back to that later at the end between sessions. So
yeah, okay.
Okay.
All right, so let's look at the research plan. And first of all, how many of you who have, just do this in the chat real quick, how many of you who have students who do research projects have already routinely been having them do a research plan prior to their starting the experiment? Let me know. Okay, I'm not seeing anybody answering yet. I got one new message. Okay. Okay, I see a reflection, but not a research plan, no research projects. Can do it. Okay. All right. So, pretty much what I'm hearing from you is what I have suspected all along. Because when you write a research plan, and some of you have been doing it, and that's great. And I see that some of you are seeing now that it is important. Most of the research plans, when you write a research plan, you're writing it before you do the experiment, which means that everything's written in future tense about I'll do such and such. And I would say that over half, about 3/4 of the research plans I review are written in past tense. And that means that they're written because we require one to be sent in. But hopefully you, through the series of sessions we've had so far, you've seen that really doing that research plan is very important, because it makes the student really think about what it is that they are going to be doing, why they are doing, having that background information. And again, it's making them go through that same process that scientists, engineers do. And it is making you and them aware of any safety issues that are out there that they need to worry about. And even if you're only doing this for your class, the research plan needs to be part of any research project that they are working on, so that they can actually go through that whole process, think about what they're doing, and then be able to say, this is what I tried, it didn't work, so now I can come back and change that variable a little bit more.
Judy,
yes.
Let me interrupt at one point, because to me, safety is the big thing. And wow, I want to know what they're going to be doing. But there's another thing. I don't know if we've been saying this, but to me, I used to ask the students to tell me their plan, and they sit down and just tell me their plan in about a minute, what they want to do. And if I didn't do that, if I didn't have them make a plan and look at it, I have seen students in other places go way down the road with their project, get near the end of their project. They've done all this work, and there might be a major flaw in the plan, something they've overlooked. Well, now they're going to really feel terrible and devastated because they didn't think of that earlier. But if they had a plan, and I don't tell them what to do, but if they have a plan, I see a big major problem, I might ask them a couple of questions to get them to think about it. And then usually they go, oh my gosh, I hadn't thought about that. I need to do this. And they'll do something that will really strengthen their plan early on. And the end result will be a lot better than getting down the road and finding out you had a faulty plan. You don't want that to happen.
Yes, I agree with all of that. And liability wise, safety issues really are in there. And you have to make sure that you have checked before you say, sure, go ahead and do it. That is something that will not cause potential harm to the student or to someone else. And that is so important, especially since this year more of our students may be doing it virtually. Knowing what they're going to be doing is even more important than before, I think. And we are planning on having regional fairs. We don't know if they'll be in person or virtual, so you can still be thinking about having your students do research projects. But it may take some adjusting with what they do to be able to make it something that is safe for them. So we've talked about the research plan. What I want, and then I think we've got the next session on here. It's not only the method, the timeline, the methods and procedures, whether they've done the rules and regulations, if all that kind of good stuff, the safety, but also, I'm going backwards too far, included in that plan needs to be, remember, the kind of data you want to collect and how you're going to analyze that data, any safety issues that are there, and how you're addressing those safety issues. And then, of course, the bibliography that needs to be included as well with the background information. Now, when I go through and review these, I'll give you some feedback and just glancing over them quickly. The ones that are easiest to read, and this is what I would suggest to you, are the ones that are written in a stepwise format. so that it's divided into sections. So you've got your question or your problem, and then you've got your materials, and then you've got your methods that you're going to be using, and then you've got the type of data you're going to collect and how you're going to analyze it, and then you're going to have your bibliography, and have a section in there, safety issues and how they're addressed. So if you're working with a chemical, you need to say that you have already obtained, the safety sheet on how to use that chemical. And that should be included in part as a bibliography, because that's information that you need to know. So these are things that we'll be looking at, and I will try to send back information to you. So what I would like for you to do quickly is think about the research plan that you submitted. How many of you, and we can do a quick voice poll on this one, how many did scientific? You can unmute yourself and answer me.
I did.
I also did.
Me
I
too.
did.
Four.
I did as well.
5. So I heard about 5 people.
Mine was
Um,
specific.
So that means about the other half of you did engineering projects. So that's interesting. Those of you who have done engineering projects, have you done them before, or was this the first time? Okay, so you can answer, but anyway, all right. So when you were doing the engineering project, one of the things that I would like to remind you when you're working with your students, you need to think about the appropriate scale and conditions. So they may be able to build something with wooden dowels or something like that, dowel rods. But when you scale it up, if they have a dowel rod that's 1 inch and you have to scale it up from something that's 2 feet to something that's 200 feet, is that going to work in scale wise when they have to multiply everything? And so, having them think about things like that as well, and whether or not they can get the kind of materials that they would need. What did you think about the rules wizard? If you can respond to that too, I would appreciate it.
I really like the rules wizard.
So did it make you feel like you were more knowledgeable about what your project was?
It gave me stuff to think about.
Okay, anyone else?
I felt
I
like
thought
it
it was
was
helpful.
very, oh, so sorry.
Okay, so everybody's waiting for the other person now, so.
There's a couple comments in the chat too, Judy, about
Right, I heard that it was user-friendly, made you think more, easy to find the info I would need for a specific project. I think it's fairly easy for students to use. I think with assistance, elementary students can answer the questions. Some of them can do it by themselves. I think it does make you aware of the fact that if you're working with humans or animals or potentially biological hazardous agents or chemical things that could be hazardous, that you can't just do it, that there are rules about the way that you work with those projects. So I think it's beneficial for you to have students do that. So did any of you who went through the rules wizard, did you have to have any special forms besides forms 1, 1A, and 1B, and the abstract and research plan?
I had to have the risk assessment form 3.
Okay, and that risk assessment form, there are some regional fairs that require every project to have that form. I know Region 6 requires that. And the reason why they require that is to make the teacher and the student look at what the project is and really examine it to see if there are any safety issues and how they will address them. Now other regional fairs and state fair will say it depends on what you're working on, and it also depends upon the grade level of the student. And I may have mentioned this last week when we were talking about safety issues a little bit, in that if a student is building something and they need to have a skill saw to cut wood, if they are a senior student, a high school student who is proficient in doing woodwork and has used the skill saw, that's not necessarily a safety issue for them because they know how to use it properly. But if you're an elementary student and you're using a skill saw, that's a huge safety risk. So you need to have either addressed in that Form 3, who's going to be running the skill saw? If the student's going to be doing it, have they been trained in the proper and safe handling of it? So that's where that Form 3 comes in, is when you're looking at what are potential risk, who's supervising it, and has the student been trained, and are you going to be comfortable? I had another one that did the human participants form. This is one that we catch a lot of those before we get to the state fair, but there's still a lot missing. When I was the regional director for Region 5 last year, in addition to the state fair director, I found many, many, many students that never even thought about doing that Form 4 and were having to backtrack and get permissions from administrators and people like that their project was okay to do. It's not the best way of doing things, but it's better than not at all. We really do, as you know, when you work with your students, if you take them anywhere or if anything is done different from what is usual in the classroom, you get parental permissions. And it's the same type thing. Anytime you work with humans, someone needs to review the project besides you and say, yes, it's okay. And we'll talk about that when we get on. I also saw that someone said that they had to do a continuation project. Continuation projects can be great for students, and it's one that I haven't touched on yet. But when you work on a continuation project, it's where you're applying the knowledge that you gained in a previous experience or skills that you gained in a previous experiment to the current one that you are doing. So you may have been doing something, trying to think. Okay, so you were doing, I'm going back to plants. You were doing a gardening plant with something, a gardening experiment, and you became proficient in the care of African violets. So you're going to do, you're going to work this time with African violets, and maybe you're going to try cultivating them to see if you can develop a brand new breed. I'm making this up. Brand new variety of African violets. You're applying the knowledge that you gained from the African violets to your new experiment. That would be a continuation project. You're not doing the same project over and over. Now there is another continuation project called a longitudinal project. And that's like you are studying stream quality over a period of years. So you're doing it basically collecting the same test as you did the previous year, but this is this year's data. The thing you have to watch out with that is the project board and all the discussion has to be on this year's data. You can talk about how it compares to previous year's data, but your main discussion has to be on this year's data and what you were seeing. You can say that there was an increase of 5% of nitrates in the water than in previous years, but you have to be talking about the data that you got this year. And that would both of these would be continuation projects that you would have to file. Also the previous year's research plan and abstract so that it shows that what you're doing this year is different from last year. All right, so any questions about those two? Okay, so I've got, it's 10:40, so I'm gonna go through these, but we're probably gonna have to stop before we get through with this and then finish it up the second week. So we do the rules and regulations that are put forth by it's now Regeneron International Science and Engineering Fair. And you should have gotten the link to all of the rules and regulations in last week. This week, I think we're sending it to you again, and we're also sending you the link to all the rules and regulations in Spanish, which are on the ISAF website. Why do we do the rules and regulations? Remember, it protects your students, it protects you and your school. Students, if they read that they're actual rules, they realize they have to actually abide by them, and they have to think through their experiment more carefully to make sure that they're doing things the way they need to be done. So you end up having a project that is better planned and executed along the way. And it really does let students understand science and engineering has rules, and it is regulated the way you do things. You cannot make up data. You cannot fabricate your results. That is something that you can be kicked out of all kinds of science and engineering societies and discredited if you are found to be doing any of those ethics violations of plagiarism and falsification of data. And I think this is really important in today's world when we're working with our students, for them to understand the value of the process of learning and about science and engineering and discovering new information. And remember, when we started the first week, both the scientific inquiry and the engineering process were both circles. And that's because as we answer one question, we're finding more questions or thinking of better ways of doing something. So it's continually being revised and rewritten. And students need to understand that it's a process and that it can change as we learn more about it. And your students may actually be going back and changing their research plans as they go through that and realize that there is a better way of doing what they were going to be doing. And so they need to revise that research plan if they change the methods and make sure that that is still approved by you. But, you know, when they talk about fake news, science and engineering should, if it's done correctly, is not fake. It is just in a stage of transition. As we learn more, we're able to add more data to what we understand. So again, I've given you these links about going to the international rules, and let me see if I can stop sharing for a minute. And if you look at, pull this up. All right, now I'm going to share a different screen. You don't really want to see my emails, but that's the one that's going to pop up. And, well, hold on. That's the checklist. There, I have to be able to move that over. All right, so if you look at ISAF, the international rules, you have this link. Here are the rules and guidelines. The forms only, all the PDF forms you can type into. They are PDF typable forms that you can save, and we do accept, and ISAF accepts digital signatures. So that's, and this is the link to the rules and guidelines in Spanish that you can do. We only have 7 categories. If you continue on that page, here's the link to the rules wizard. Manly's going to talk about display and safety rules. And here's an overview of the forms and dates. And here's some, and that's also found on our website. So our website has a list of all of the different forms. And it talks, here's a flow chart if you want to go through that. It was designed by Dr. Rachel Graham, who is head of our scientific review committee. She is also a researcher at UNC, and her area of research is on coronaviruses. So needless to say, she has been extremely busy since February, working on all of this. But we have put in there who needs to fill out the form, directions about doing it, description about what the form is. And this is a link. This is updated. We have an abstract, and we'll talk about abstracts. That's the North Carolina abstract that can be downloaded at this plan. There is no form for the research plan. That should be in the journal, but the back of Form 1A, which I also sent that to you last week, gives you information on what should be in a research plan. So let me stop sharing that. Oh, let me look. Okay, I'm moving quickly. All right, so now I'm going to stop sharing that and go back to the forms. And let's talk about those. Every year I kind of go, oh my gosh, there's so much paperwork. I hope that you thought about looking at the forms that when you did the Rules Wizard, to be able to see what it is. If you look at these forms, 1A, and 1B are required for every single project. And when I was in the classroom, I remember I had a paper allotment, and I couldn't print out all these forms for 300 students because that would blow my paper allotment completely. So I'm going to show you a sample Google form that I created that asks the same questions as these 3 forms. And you can, it will, you get a time and date stamp to be able to get the parents to do it. And then you as a teacher would do one for each project. And then those students that move beyond your school onto a regional fair would need to fill out the paper forms based on the data that you have in the spreadsheet that you get from the Google form. So if you look at Form 1, the top portion of that, it talks about, basically it asks the student's name and the project title. You have to check that you have reviewed the rules and regulations and science fair ethics statement. You have to check that you reviewed the students completed 1A and their research plan. You have to check that you've worked with a student and talked about possible safety risk involved in the project. And then you have to check if it involves one of the things that would require a prior approval by either someone who's knowledgeable about animals or safety issues with the scientific review committee or humans with the international IRB committee. And if none of those are fine, you can skip that. Then if you checked any of those, then that where it says additional forms required, it goes into detail about what is required for the projects that require prior approval. And then it's signed by the supervising teacher and with their email, their date, and their phone number. If you look at Form 1A, this is the student's version of that, where they put in who's the team leader. If it's a single individual project, only one of them does it. If it's a team, and teams can be up to 3 people, please do not send a team of 4 people because we have to disqualify them because that's an ISEF rule that we have to enforce. So maximum of 3 people on a team, please. All the team members' names, the working title for the project, this can be changed, what school they go to, contact information about the school, who's supervising them. So if you're the supervisor, that would be your information, whether it needs pre-approval or not. And that goes back to, is it humans, animals, potentially hazardous materials. And if it's a continuation form, so then, or whether it's, and then when they plan to start the experimentation. Now, this date is not the date you start at the beginning year, finding the topic, developing that question or problem, and then during the research plan. This date is when they actually start experimentation. This year, that might be very important for your students. With virtual fairs, it may be that a student may want to start a project, but may want to continue working on it longer if your school's not able to have their fair. The ISEF rules and regulations that we enforce and that we use state that a student can work on a research project for up to 12 months within an 18-month period of presenting their research to the competition. So that means if you've done all this development time and they haven't actually started experimenting till November or December, if you go, they could actually do work on it for a full year and then present it within 6 months after that, which means they could present at next year, not this coming year's, but the following year's competition. So that may be something that may come into play more this year with the virtual schools and the
Right,
virtual
Judy.
classrooms.
Oops, sorry to interrupt. We are at 10:50. Is this a good stopping point so we could start with demoing the forms in the next session?
Let me say one more thing about 1B. And basically that will take me only 1 second. Not 1 second, but less than a minute. Form 1B is where you get the parent's signature that they have read the student's research plan and they've looked at the rules. And the student signs it as well. And I know good and well that most of these parents have never looked at the rules. And so that means that they will sign it without reading it, even though it says that they've read it. That puts even more responsibility on this teacher that is supervising to make sure that it's safe, because the parents, even though they're signing something that says they've read the rules, they will be depending upon you as the supervising teacher to make sure the student does something that would not be harmful to them. The second part of it is if it's something that requires pre-approval, like human subjects or animals or hazardous materials, has to be signed there. So only 1 and 2 would be something that you would look at on 1B. Research plan we've already talked about, and abstracts we're going to talk about a little bit more. When we get back after the break, and I'll be staying here, and we'll switch over and open up, and I'll show you the 2 sample Google Docs that I have made. These are live links to them, so that these are samples that you can do for your students for research that they are doing in your classroom. Okay, so we will sign out and I will talk to you later.
All right, thanks everybody. Just remember, pop back into the next link by 11, please, and we will get started. Thank
And
you.
email us if you do not have the link or if you're having problems. Thank you.
Yes.